Now that we know that momentum is conserved for an isolated system, we're going to use this fact to actually solve some individual problems. So looking at conservation of momentum, we know that when two objects come together, okay, that they're usually going to, on contact, going to put an equal and opposite force on one another. What this contact is created by, normally it's the repulsion of the electrostatic forces of the electrons on the surface. Maybe they are charged and they don't even make contact, that they come close enough to put an electric force on one another. Maybe it's a magnetic force. Whatever the interaction is for this closed system, an isolated system without external forces is going to conserve momentum during this interaction. So what we can say here is we can say that by Newton's third law, for every action, there's an equal and opposite reaction. So the force on one due to two is going to be equal and opposite to the force on two due to one. Basically, the impulse that one experiences is going to be equal, but in the opposite direction of what two experiences. And therefore, we can write those two expressions this way. So again, looking at this, we can see that by Newton's third law, for every action, there's an equal and opposite reaction. For every impulse, there's an equal and opposite impulse. And thus, the change in momentum of the entire system for an isolated system, where the external forces are zero, is going to add up to be equal to zero. So that makes it very easy to take a look at an interaction, add up what the momentum is before the interaction, add up what the momentum is after the interaction, and essentially find out anything that might not be known. So again, our net momentum change is going to be equal to the momentum change of the first object plus the momentum change of the second object. That's going to add up to be equal to zero. I can rewrite this equation. We can say that delta P1, the change in momentum of this red ball, is going to be equal to its final momentum minus its initial momentum, plus the change in the momentum of the green ball, final minus initial. This is going to all add up to be equal to zero. Rewriting the equation a little bit, we can clearly see that the momentum before the collide is going to be equal to the momentum after the collide, and we get this nice expression right here, where again, we can use this expression to find out some unknown. Maybe I have two balls coming in, they collide. I know the momentum of the second one, but I don't know the momentum of the first one. I can find that unknown by solving this equation. Let's do an example here. This is going to be, as we're going to see later on, this is what we call an inelastic collision, in that some of the mechanical energy is going to be lost during the collision that takes place. Two objects are going to come in, they're going to collide, and then they're going to stick together after the collision. So we have two freight cars. The first car is traveling at a pretty good speed, 8 meters per second. And as it makes contact, the coupling is going to lock and the two will move together afterwards. So this is a very good example of an inelastic collision here. So we look at the momentum of the first car. We have a mass of 30,000 kilograms. We have a velocity of 8 meters per second. That is going to give me a momentum traveling in the positive x direction of 240,000 kilograms meters per second. The second car is not moving. It's stationary before it's coupled with the first. So here, even though the mass is the same, the velocity is zero, so its momentum is zero. So the momentum before the interaction, the momentum before they collide, is going to be equal to the momentum after the collision. So now I can find out an unknown. How fast are they going to be traveling afterward? Well, common sense is going to tell you that if you come in with X amount of momentum, okay, and suddenly you distribute that momentum among two cars of equal mass, okay, you're doubling the mass in a sense. To conserve that momentum, you're going to be going half as fast. In fact, let's do that right here. Here's our initial momentum of the red car. Here's the initial momentum of the green car, which is zero. So 240,000 kilograms meters per second is going to be my initial momentum. And I've got to be a little bit careful here. This should have been V1I. Okay, yeah, V1I is here. Again, my velocity of the first car and the second car, I'm requiring them to move together because the coupling has locked. So again, 240,000 plus 0 is going to be equal to 240,000, which is also equal to the total momentum of the two cars after, 60,000 kilograms times VF. VF is my unknown. It's a velocity of 1 and 2 after the collision, but again, they're locked together. And, just as I suspected, I'm going to drop from 8 meters per second to 4 meters per second. Okay, let's try something a little bit different. I'm going to change the mass of the second car, and let's see that I'm going to get a different velocity for my final outcome. I'm going to make this a little more massive. So when I do that, I get the same basic momentum before and momentum after. The only difference here is that my final mass of the green car plus the red car is going to be 80,000. So again, I solved this just the same way I did before, 240,000 kilograms meters per second. This is 0. And here I have a slightly larger mass than I did before. 240,000 kilograms meters per second divided by 80,000 kilograms now gives me a new velocity of 3 meters per second. And that's what we expect. We're more than doubling the mass of the entire combined system when they lock together, the system being, car 1 and car 2. And as a result, we're going to be traveling slower, but still have the same momentum that we had before. Now, conservation of momentum is basically how we can actually maneuver once we're in orbit. Think about it this way. A rocket has nothing to push off of. If I'm in a car, I can push off the ground. If I'm in a plane, I can push off the air. But in space, there is nothing to interact with. So essentially, we have an isolated system. We can't put an external force on the rocket. All the forces are going to be internal for the system. So how do I propel myself once I'm up into space? Well, here, I will take the initial momentum of the rocket and the momentum of the gas, which is going to use to propel myself, basically the fuel. Now, initially, when the thrusters are turned off, the total momentum of the system in the frame of reference, obviously the rocket's probably moving somewhere, but in this frame of reference, which is going to be approximately inertial, although when you're in orbit, it's not really a true inertial frame of reference, but we're going to behave like it is. We have 0 momentum before, and that's going to have to be my momentum afterward. But you notice that the forward momentum that the rocket is going to gain is going to be equal and opposite to the gas which is given off by the thrusters. So initially, I start like this. Afterward, my total momentum is still 0, but I can give momentum to the rocket by giving off gas in the opposite direction. And this superheated gas, the hotter it is, the more momentum I'm going to have per kilogram of fuel that I expend. So what we try to do is we try to create a very, very hot gas, which is going to have a very, very high velocity. In this particular case, I'm going to use a bipropellant gas. Maybe I'm using hydrolox, hydrogen and oxygen, which give off about 4,000 meters per second exhaust velocity. And if I look at this, once again, I'm going to solve for my final velocity of the rocket. I'm initially stationary with respect to wherever I am in space, and I want to change my velocity a little bit. We'll see that helps us change our orbit. Again, an orbit's not a truly inertial frame, but we're going to treat it like that. So my final rocket velocity is going to be equal to the mass of the gas which I'm giving off divided by the mass of the rocket, Okay. In fact, I'm probably not doing this um, the proper way. We're going to use the rocket equation to really properly analyze this, because if I'm losing for the kilograms of fuel, I'm going from 2,000 kilograms to 1960 kilograms. But in any case, I'm going to act like everything stays constant. And in this case, you can clearly see that with the negative thrust of the gas expanding in the backward direction, I can propel the rocket forward and I get a velocity of 80 meters per second. Again, to truly treat this in a proper way, because the mass of the rocket changes as I give off exhaust, I have to use something called the rocket equation. And that's going to be a little more complicated than what we see here. So again, we think about the impulse on rockets. The impulse is provided by the escaping gas downward. And the faster that gas can escape, the more momentum, more impulse I can transfer to the rocket with using less and less fuel. So that's why typically with these rockets, we want to use a very, very energetic chemical reaction to propel them. Let's use the example of recoil. Here I have a 5-kilogram rifle, and it's going to shoot a 20-gram bullet at a speed of 620 meters per second. Now, you're going to see that when firing a weapon, a firearm, the recoil of the firearm is not insignificant. So again, we're pretty much acting like the rocket system. Before the interaction, both the rifle and the bullet have zero momentum, at least in our frame of reference. After the bullet is fired, the momentum of the rifle and bullet has to be equal and opposite. So calculating this, we make the rifle equal and opposite to the change in momentum of the bullet. Therefore, the rifle's recoil, the bullet is going to be pushed forward, the rifle is going to kick back. If there are no other forces on this rifle, it is going to recoil at negative 2.5 meters per second. That is why if you look on a rifle, the scope, the optics of the scope is set so it's far away from your eye. So if somebody inexperienced fires this and they have their eye right up to the scope, it's going to give them a pretty good injury right there. They're going to get a significant black eye from this. So what we typically do is, this is the recoil pad on the rifle. We put that right up to our shoulder, and when this fires, what happens instead is, instead of the rifle recoiling, the entire body recoils. So if an 80-kilogram person now fires this rifle, the recoil speed, instead of being 2.5 meters per second, is going to drop down to 0.15 meters per second, because the rifle is securely connected to their body, and that prevents injury. Let's go back to something we did before. We looked at the USS New Jersey firing one of its main guns, and we saw that the velocity of the projectile was such that it gave it nearly 1,000,000 kilogram meters per second of momentum. Talking about the shell that's being fired. What would that do to the battleship itself? Well, the battleship itself, these turrets can actually recoil. They actually have a suspension that allows them to recoil. But in terms of the total recoil of the ship, because the ship is so massive, if I have this correct, it's 40 million kilograms. The recoil velocity would be really, not very large at all. Now, the barrel itself would have a significant recoil velocity, but the ship itself, by conservation of energy, is not going to really be deviated very much by this recoil.